And for this example, we went through very simplistic versions of looking at the gears, where I've been drawing them as circles. We took that statement saying that we have the force working in, force going out, and it's actually not as simple as that. So if we wanted to design a gear, so if we do want gears to work like that, and they can work like that, but now if I told you to go make a gear, and you went and drew me some gears with straight teeth, they actually would not work at transferring the force, because when the teeth were in direct contact as I drew them, it would have that force and velocity relationship. But whenever we were in a point where the teeth were not in that same connection point, so at any points beside when they were flat up against each other, then the velocity of the driven gear would not remain constant. So we could say that this is not going to work. And that straight teeth would not allow for a constant gear ratio. It would instead be a function of our angle. So we're going to let ourselves know that the teeth on the gears they need to be curved in order to allow for a constant gear ratio. So if we want to have that nice connection that we discussed in our previous videos, where we can say that we have two circles that are essentially connecting with each other, then where we have some radius here, we have some radius here, and we can say that our points A and B can be represented by their interactions at point P, then what's going on is that we have these involute curves, and I'm going to have a little bit of a rough time drawing this because it's hard to draw a nice curve. But you want to have it so that we can assume that we can say that the force that's affecting the torque is constant, because it's going to work across a line of action so that the torque remains constant and the relationship remains constant. So we're going to have that we have a force that's operating down, then we have some force that's transitional, some force that's normal, and that they operate at the pressure angle alpha. And in order for that to happen, we need to use what's called an involute curve. So we would say that our base angle would be what we would use to draw that. And if you take a length and we say that we want to curve it around, and we want to track the end of this thread here as we put it and pull it around our device, that path would look a little bit like this. And when we draw our teeth on our gear, we're going to draw it so that they follow those paths, as if we had a curve string that was going around, and that would allow us to travel through. And I should draw that the curve goes through kind of the middle, but when we have our when we have the radius of our gears, it's going to be somewhere between that base angle and our involute curve. And I'm going to show you a better drawing because this is not an easy thing for me to draw. So let's go to the next page. And here, when we want to see what's going on, here we have some gears with some nice involute curves. So we see that they have a curve to them. And this line here is called the line of action, because that's going to be the line at which our force is occurring on our device. So right now, at this point right here, it's going to transfer as the device moves around. But we can see that there's a reactionary force operating at this point, and that it's operating at an angle of our pressure angle of alpha. And that is equivalent to us being able to say that we have some radius, our RP, we have our arc, which is that radius caused by P, the pitch radius. And we can say that there is our, so here we have our W, our normal force that doesn't affect our torque, and that this is happening at that angle of attack alpha. And so we can say that our torque is equal to W crossed with RP. Our normal is going to be W tan alpha, and alpha is our pitch angle, is our pressure angle. And we often don't deal with F. So like if we wanted to label this as our F, which we see in the book is here we have F and minus F as it occurs on our gear. But it can be important to know. So we can say that F is just going to be that square root of W squared plus N squared. And that's going to be the force on your bearing or shaft. So not a problem when we're just looking at the dynamics, but as you get into machine design later on in your career, you're going to say, oh, well, we need to consider that so that we make sure it's strong enough. So that'll be the force on the shaft. And in this diagram of the gears, some things to note. So here we have our RP of one gear. Here we have the RP of another. And then our RB would be this curve here. And here we have that this RB is over here, according to this label. And so RB2. And we see that we have different dedendums. I'll talk about those in a little bit. They're not as important for you to know right now, but we can still have them discussed. So here we'll have RP according to that center. And this is the dynamics that allow the gear to rotate. So let's go through, talk about a little bit more details on that.